Next chapter, reflection at curved surfaces. Now, we looked at reflection of light and image formation on plane surfaces in Form 1. In this chapter, we shall look at reflection of light and image formation on curved surfaces. For example, a spoon. It has two reflecting surfaces, one is curved inside and the other is curved outside. However, spoons are not perfectly spherical. So for easy understanding, let us talk about spherical mirrors. A spherical mirror is made from a hollow glass sphere. In other words, it is a plain glass bulging inwards or outwards. Just like the spoons, spherical mirrors are classified as convex and concave. A convex mirror reflects light from its outer spherical surface and has a silver coating on its inner surface. They are normally used as driving mirrors in vehicles. A concave mirror reflects light from its inner spherical surface and has a silver coating on its outer surface. They are used by dentists to examine teeth. First, let's talk about the terminologies used in curved or spherical mirrors. First, they are called spherical because they are a part of a sphere. Center of curvature C is the center of the sphere of which the mirror is a part. Radius of curvature R is the radius of the sphere of which the mirror is a part. Pole P is the geometric center of the spherical mirror. Aperture is the surface of the mirror used for reflection. Principal axis is the line joining the pole and the center of curvature. Principal focus F is a point on the principal axis where rays of light after reflection converge at or appear to diverge from. Focal length F is the distance of the principal focus from the pole of the mirror. So let's now talk about reflection on curved mirrors. We start with convex mirrors. Now, the behavior of light rays reflected from a convex mirror vary based on the angle of incidence on the mirror. In curved mirrors, a normal is a line incident on the mirror directed towards C. In this way, a ray of light incident on the mirror and directed towards C is usually reflected along the same path. In this case, the incident angle is 0. Secondly, a ray of light parallel to the principal axis is reflected in such a way that it appears to be coming from the principal focus F. Thirdly, an incident ray directed towards the principal focus is reflected and emerges parallel to the principal axis. Finally, an incident ray at the pole at an angle with the principal axis is reflected at the same angle with the principal axis. Now, concave mirrors. As in the convex mirrors, reflection of light rays in a concave mirror also follows certain laws. 1. A ray parallel to the principal axis is reflected and passes through the focus. 2. An incident ray passing through C is reflected along the same path. 3. An incident ray passing through the focus is reflected parallel to the principal axis. And 4. An incident ray at an angle at P is reflected at the same angle. Now let's talk about the formation and characteristics of images on curved mirrors. Now, ray diagrams can be used to explain how images are formed by spherical mirrors and their characteristics. We start with concave mirrors. When a beam of light parallel to the principal axis is incident on the reflecting surface of a concave mirror, its rays all converge at a point on the principal axis. This is usually the principal focus of the mirror. The nature and size of image in a concave mirror depends on the relative position of the object from the mirror. Let us start with an object at infinity. The image is formed at the principal focus. This image is real, inverted, and highly diminished in size. Next is an object just beyond C. We usually draw two rays which are usually enough to tell us the position of the image. And because the image is resting on the principal axis, all we need is the top of the image. So, first ray, a ray parallel to the principal axis. This is reflected to pass through F. Second ray, a ray through F. This one emerges parallel to the principal axis. Where the two rays meet is the top of the image. And even if we draw a third ray, for instance through C, it will be reflected back through the same path, and all the three meet at the same point. And so, for an object beyond C but not at infinity, the image is formed between C and F. It is real, inverted, and diminished in size. Next is an object at C. First ray, a ray parallel to the principal axis. This emerges and passes through F. Second ray, a ray through F, and this one emerges parallel to the principal axis. The image is here. And so, for an object at C, the image is formed at the same point. It is real, inverted, and the same size as the object. Now an object between C and F. First ray, a ray parallel to the principal axis. This is reflected through F. Second ray, a ray incident through F. It emerges parallel to the principal axis. The image is formed beyond C. It is a real image, inverted and magnified. Now an object at F. First ray, a ray parallel to the principal axis. It emerges through F. Now we cannot draw a ray through F. So our second ray will be one through C, and this one retraces its path after reflection. The reflected rays appear to be parallel, so the image is formed at infinity. This image is real, inverted, and highly magnified. Finally, an object placed between F and the mirror. First ray, parallel to the principal axis. It is reflected through F. Second ray, through F. This one is reflected parallel to the principal axis. Now, on this side, the rays appear to be diverging. If we extend them on the other side, they converge here. So the image is formed on the opposite side of the mirror. This image is virtual, direct, and magnified. We move to convex mirrors. Now, when a beam parallel to the principal axis is incident on a convex mirror, it is reflected and its rays diverge and appear to originate from the principal focus when extended backwards. The image formed by a convex mirror is always erect, virtual, and diminished in size. The location of the object does not affect the characteristics of the image, unlike in concave mirrors. Therefore, as the object approaches the mirror, the image approaches the mirror as well, though not proportionately. Note that during image formation, a familiar pattern is seen. For instance, when the object is at infinity, the image is formed at F. And when the object is at F, the image is formed at infinity. When the object is beyond C, the image is between C and F. And when the object is between C and F, the image is beyond C. We call this the principle of reversibility of light. Next, we move to linear magnification. Now, the ratio of the height of an object in a spherical mirror to the actual height of the object is called linear magnification. This is denoted by the small letter m. You can determine the size of an image reflected in a spherical mirror by using linear magnification. Magnification can also be computed as the ratio of the image distance to object distance. Thus, the ratio of the image height to the height of the object is equal to the ratio of the image distance to object distance. Magnification can be 1 or unity, greater than 1 or less than 1. Magnification is equal to 1 when the image size is equal to the object size. Images formed in plane mirrors are the same size as the objects. Therefore, the magnification in a plane mirror is equal to 1. In other words, there is no magnification. Magnification is greater than 1 when the image size is greater than the object size. For example, the image of an object placed between C and F of a concave mirror. Magnification is greater than 1 and the image is said to be magnified. Conversely, magnification is less than 1 when the image size is less than the object size. For example, when an object is placed beyond point C of a concave mirror, the image is said to be diminished. The mirror formula. Now, suppose an object is placed in front of a concave mirror 30 centimeters away. The focal length of the mirror is 10 centimeters. How can we find the position of the image without construction? Now, the image distance, object distance, and the focal length in a spherical mirror are related by the mirror formula. 1 over f is equal to 1 over u plus 1 over v, where f is the focal length, u is the object distance from P, and v is the image distance from P. All distances are measured from P. Distances of real images, real objects, and real focal length are considered positive, while distances of virtual objects, images, and focal length are negative. So for our case, 1 over 10 will be equal to 1 over 30 plus 1 over v. Rearranging to make 1 over v the subject of the formula, 1 over v is equal to 1 over 10 minus 1 over 30. The LCM of 10 and 30 is 30. So 30 divided by 10 is equal to 3 times 1 is 3. 30 divided by 30 is 1, times minus 1 is minus 1. That gives us 2 over 30, which is equal to 1 over 15. And so 1 over V is equal to 1 over 15. Taking reciprocal on both sides, V is equal to 15 centimeters, and that is the image distance. What will be the magnification? It will be image distance V over the object distance U. That is 15 over 30, which is 1 over 2 or half. So the image is twice as small as the object, or in other words, it is half as big as the object. Let's take an example. A bulb 4 centimeters tall is placed 30 centimeters in front of a convex mirror of focal length 12 centimeters. Determine the image distance and the image height. Now in this case, we have a convex mirror, which means the focal length is virtual. And that means if you look at this convex mirror, the reflected rays appear to diverge from F behind the reflecting surface. In reality though, these rays do not exist. There is nothing behind the mirror. So the object height H0 is equal to 4 centimeters. The image height H1 is unknown. Object distance U is 30 centimeters. The image distance V is unknown. The focal length F is negative 12 centimeters. 1 over F is equal to 1 over V plus 1 over U. That means 1 over negative 12 is equal to 1 over V plus 1 over 30. So 1 over V is equal to 1 over 12 minus 1 over 30. The LCM of negative 12 and 30 is 60 or negative 60, but let's use positive 60. 60 divided by negative 12 is negative 5, times 1 is negative 5. 60 divided by 30 is 2, times negative 1 is negative 2, and that gives us negative 7 over 60. So 1 over V is equal to negative 7 over 60, and V is equal to 60 over negative 7, which is negative 8.6 centimeters. And that means the image is virtual. It is formed behind the reflecting surface. How about the image size? We know that H1 over H0 is equal to V over U. And therefore H1 over 4 is equal to 8.6 over 30. We cross multiply. 30 times H1 is equal to 4 times 8.6. That gives us 34.4. We divide both sides by 30 to get H1. That gives us approximately 1 centimeter. Now, let's talk about the relationship between the focal length and the radius of curvature of a spherical mirror. The focal length of a spherical mirror depends on its radius of curvature. Consider a ray Q parallel to the principal axis incident at point M on the mirror. The incident ray is reflected in accordance to the laws of reflection. When the reflected ray is extended beyond the mirror, it meets the principal axis at point F, which is the principal focus of the mirror. We know that angle I is equal to angle R. Angle I is also equal to angle MCF because they are corresponding. Additionally, angle R is equal to angle CMF because they are vertically opposite. Thus, angle MCF is equal to angle CMF. And therefore, CF is equal to MF. If point M is very close to point P, that is the linear aperture of the mirror is very small, then MF is equal to PF. Thus, CF is equal to PF. Also, PC is equal to PF plus CF, or PC is equal to PF since CF is equal to PF. Therefore, R, the radius of curvature, is equal to 2 PF. But PF is the focal length of the mirror, and therefore R is equal to 2F, or F is equal to R over 2. And therefore in spherical mirrors, the focal length is usually half the radius of curvature. Next, graphical analysis of the mirror formula. Now, the mirror formula can be rearranged as follows: 1 over U plus 1 over V. The LCM of U and V is U times V, or UV. UV divided by U is V, times 1 is V. UV divided by V is U, times plus 1 is U. So 1 over F is equal to V plus U over UV. Getting the reciprocal, F is equal to UV over V plus U. If we had several pairs of U and V values and plot a graph of 1 over U against 1 over V, we shall have a linear graph like this one with a negative gradient. And this means the image will be inverted relative to the object. In this graph, both the X and Y intercepts give 1 over F. But a graph of UV against U plus V gives a linear graph through the origin with a gradient equal to F. Finally, applications of spherical mirrors. Convex mirrors are used as driving mirrors in vehicles. The objects seen in these mirrors are closer and larger than they appear. Concave mirrors are used as dentist reflectors. They help to enlarge the images of faraway objects or to view objects that you cannot directly see due to their position. Dentists use them to view the inner side of the mouth with more clarity.